handle these details in the lecture part. So a brief theoretical introduction about data acquisition, and then we'll do some simulation of data acquisition. That is very simple. So let's just confirm that it is available on e-learning. Okay, in the e-learning you'll see the manual, the assignments, but not the VI. Okay, so let's add that. Okay, so basically this VI we will do some simulation of data acquisition. That is very simple, and we will answer the questions provided in the manual based on that VI. Okay, and then after we simulate, we will go to real acquisition. Now the camera is open. I suppose all of you can see the camera. And let's confirm the clarity of the image you can see. Okay, sure. So can you please confirm the image? Can you see my hand now?
Yes, Doctor, we can see your hand.
Perfect. Okay, so I'm not sure how clear. All right, thank you. I'm not sure how clear its low resolution. Okay, so okay. All right, so because this is a little bit away from the device, now when I explain anything in the device, I will zoom the camera. In addition, I've made HD video on YouTube explaining the connections of the device. So these are very simple. Not clear, okay, so we will handle this. If at the end of the lab, if you're not satisfied with the clarity, I will make another YouTube video. There is already a YouTube video explaining the connection, but I will make more videos on that, explaining the device and how it works. So today's lab and the next one, labs number 5 and 6, we will be dealing with the LBIS board. Okay, so basically, actually all of them will be in LBIS board, but today we will not put any add-on on the board. We will deal with it as it is. In labs number 7, 8, 9, and 10, we will plug in other instruments or add on boards, and we will do experiments on those. Okay, so basically the idea, we will be dealing with LBIS board from now on the lab. Okay, so let's discover the manual. Let me see. All right, so this is on the e-learning shop. You have the manual, a VI, and a report template. Okay, so all of you are supposed to see these three things: manual, sampling simulation VI, and lab5 report template. Okay. All right, so I will share my screen. Leave this. All right, so basically now you have two things: the camera and the screen. Which one you see, Shabab? Do you see my screen or the camera? You can choose. Okay. Perfect. So this is nice. All right. So I'll open the manual. Okay, so let's discover the manual. Okay. So here the manual, we have basically, I'll summarize what you need to submit at the end. Okay, so if you go to page number What's the page number? Okay, so if you go page number 6, you'll see exercise number 1. Now, generally, you have these underlined questions or instructions. Now, for these, you have to provide an answer in the report template. So, for example, step 1 says provide a complete screen capture. Now, at this point, I will open my report template. Okay, so this is the report template, and step number 1, exercise number 1, I will provide my capture here. So basically, you have to fill in the answers in the manual, or the questions from the manual. You have to answer them here in the report template. Okay, so basically, you will fill this template with captures and some answers, and at the end you will submit. Okay, just submit this report template. Okay, so you understand what you need to submit at the end? The template with captures and answers. All right, perfect. All right, so let's delve in lab number 5 now. Lab number 5 will address the data acquisition. Okay, let me open the Word. Can easily draw in Word. Okay, so we'll handle data acquisition. Data acquisition is very simple. There are some foundational theoretical details about this data acquisition. As I said, we will just address those very briefly. Okay, basically the principle of sampling. Okay, so what is data acquisition? Now, data acquisition will focus on measuring signals. Let's put some red color here. Okay, so measuring signals from real world and then digitizing those signals for analysis, storage, and display for user. So basically, I'm doing some measurement. Okay, data acquisition, meaning I'm measuring something. All right, so what is this thing? Here I can see that I have the word signal. So basically, I have a signal. We will see what that means, and I want to acquire that signal. Okay, so when I acquire, meaning I'm measuring or converting this signal into a form that the computer can handle. So I have a computer here. Okay, so here I have a computer. Okay, so basically the first thing I have is a signal, and the second thing is my computer. So basically I'm using my computer to acquire a signal from the real world. Okay, so this is a simple definition of data acquisition. All right, so what is a signal? Here in this figure, I see the complete cycle of data acquisition system, or the complete components of the data acquisition system. Okay, so in general, you begin from here, from physical phenomena. You want to measure this physical phenomenon, and then you want to store it, or you want to display it for the user, or you want to use it in a feedback loop, etc. So you have a physical phenomenon. Okay, an example of this physical phenomenon is, this is where I need to write. For example, on on this physical phenomenon is what? Let's see an example. You have stress. Okay, you can measure stress and consequently strain. Actually, they are interchangeable. Measuring one means the other. Okay, you can measure speed. You can measure mass. You can measure acceleration. Okay, you can measure wind speed. Who can provide me with more phenomenon that we can measure as mechanical engineers? What? So you can measure flow rate. Okay, and many things. Okay, now for each one of these variables or physical phenomena, we have a sensor. Okay. Now the sensor simply will convert this physical quantity here or physical variable into a variable that I can acquire by a computer. Okay, so basically I have my sensor here. This is my sensor. Okay. Now there is a difference between sensor and transducer. Basically, we'll use a sensor. Transducer is very generic name, but to measure something, you need a sensor. Okay. So the sensor simply will convert the physical variable that you have on this side into electrical signal. So basically here I have some electrical signal. All right. Now this electrical signal is often contains some noise. There's some noise and there is many defects in this signal. So the need for signal conditioning will arise then. Okay, this is signal conditioning. Now, an example of signal conditioning is to use filters. Okay, so this is the conditioned signal here. I have used the filter Okay, the filter took this noisy signal and gave me this clean signal, right? Now, when my signal is filtered and ready for acquisition, I will use the analog to digital converter. Okay, so let me look at this. Now, this is my concern today is let's put this in order. This is my interest today, is the analog to digital converter. Okay, simply the analog to digital converter will take a signal from here. Okay, so this is usually electrical. With the letter E like this, and it will convert it to a form that I can see here. Okay, so this is electrical. Here I see digital. So this is my digital. My digital signal. Okay. All right. So we will not go in depth about these analog to digital converters. Again, they have some theoretical ground to investigate and to understand them in depth. But as a user, me as a mechanical engineer, I'll focus into the use of these devices. Okay, more than the foundational theory of them. Okay, so objective today is to be able to understand the basic terminology involved in these analog digital converters and how to handle the digital form basically. Okay, so this is very all right. The cycle can further develop into a driver software. Now we have your signal in digital format. It means you are working in another domain, the computer domain. So you can use a software to store or to display or to do whatever you need with your data. Basically, you will use an application software to do this. All right. All right, so our application software today, we will use what you call in the past we used LabVIEW, but this semester we will not use LabVIEW. We will use what you call measurement live soft panels. So we'll use web-based soft panels. Okay, and another example on this application software is you can use LabVIEW which is very powerful. You can use MATLAB. You can use Simulink as well. So you have a lot of software. All right. Okay, so this is very simple introduction about data acquisition. Simply you will have analog world and here you have the digital world. Okay, so to convert from here to here you have some limitations. You have okay. Sensors here we will deal with this in lab number 7, I suppose. We have 2 labs on this. We'll deal with sensors. Signal conditioning, we will not deal with this because it is electrical topic. Electrical engineers will deal with this. Filter, signal conditioning. Analog digital, this is my concern today. All right. This side here, you are already familiar with it. Knowing what you know by now about LabVIEW, this is already established for you. Okay. All right. So this is again a simple introduction about data acquisition. All right. So this is summarized here in these theoretical or these basically jargon statements. Now one thing, okay, this literature is very useful. The difference between sensors and transducers. Okay, in general, transducers convert energy, and they don't have to be for measurement. An example is motor. Motor is considered as transducer. Okay, while sensors are specific for measurements. Okay, this is just general literature for you. So transducer and sensors, they are not the same thing. This is number one. All right. Signals. All right. So, what is a signal? Now I will go. Go to this one note here, and at the same time you can access this one note from the teams here, lab number 5. If you go to this one here, you can open whatever we write today. It is already synchronized with this tab. Okay, lab number 5, and you'll see whatever we write here in the note team. Okay. All right. So, what is a signal? Let's put some simple definition. What is a signal? Okay. Anybody have an idea about the definition of a signal? Yeah, temperature is a signal. Okay. But like the definition of a signal. All right. So a signal is physical variable that changes with respect to time. Okay, and this is my main concern. This is very important when you're dealing with data acquisition, is to consider the timing of your acquisition, okay, with respect to your signal. All right. So what does this mean? Let's take examples on this, and we will see the importance of the word here. Okay. An example on a signal. Okay. Is the mass a signal? Does the mass change with time? A mass of a body, let's say a mass of your car, or a mass of a wheel, or whatever. Right. Now this is simply because the mass is not changing with time. Unless it does, then you have to consider it as a varying parameter. Yeah, but in general, mass is not a signal. All right. Now imagine that you have a beam like this. Okay, the beam is fixed here, and I don't know, let's put here a pivot like this. Okay, and here you have a force. Alright, now if you consider the vibration of this beam, now this is a signal. If you see beam vibration, yeah, this is a signal. Now beam vibration, let's say that displacement, I'm measuring displacement. In that sense, you will have your displacement x. Say I'm measuring from this reference, my x like this. Now x will be a function of time. Okay, so basically this is truly a signal. Okay, simply because this is changing with time. Still, I'm not measuring this distance or the vibration. Okay, as a mechanical variable here, it is considered as a signal. Okay, and so on. Temperature. I don't know if you have engine temperature like this. Engine temperature. Okay. Now, if your temperature is dynamic, then I consider it as a signal. Okay, so in general, yes, it is a signal. Say I'm measuring T engine as a function of time. Right. So what do I need from this? I need to remember that this T here and this T here, okay, these mean that I have a dynamic phenomenon okay. Measurement wise, I consider these as signals. Alright, so I suppose this is clear. A signal is something that is changing with time. Okay, this is why here in this diagram you always have it says here a signal, you have a signal, etc. Okay, sure. Alright, let's put separator here. Now this is just about a signal. Alright. Now signals can be, I have to distinguish, analog. They can be analog and they can be digital. Right. This is theoretical topic, but to keep things in order, I'm going to give you a simple definition of this. So analog versus digital. I'm going to draw a signal here. Let's put a blue line. Alright, so I have a signal like this. So basically I'm plotting here a sine wave. Let's say I have sine omega t, right? I suppose all of you are familiar with this from vibration or from dynamic systems, probably from controls. And this is x, x as a function. Okay. Alright, so here at any point of time, at a generic point of time t, you have a value of that signal at basically x of that t, right? And this is true for all values of t, right? And basically this is a property of analog signals. So to define analog signal, it means the value of the signal to put this simply without mathematics, or let's say the signal itself. Let me delete this. The signal can take any value. This is the meaning of analog signal. Okay, so basically here, mathematically, you'll say that x of t belongs to real numbers, like this, right? Okay, so up to now, I'm not considering the time. I'm not considering anything about time. I'm just talking about the x-axis here, okay? And the value of my signal, where this is plotted on the x-axis or on the, you can say, the y-axis. Now, the value of this signal x of t can be anything. Okay, can be any real number. Okay, so this is an analog signal. What about digital? Say digital signal. The signal value is discrete. Signal value is discrete. In other words, signal can take a value of a specific set of values. Okay, so basically here, if you are dealing with digital signals, you have only some set of possible values. These are the ticks I am marking now. The signal can take only one of these values. It cannot be anything between. So this is analog versus digital. Tamam. All right.
Doctor?
Yes.
I have a question. What's the relation between the analog and diagonal and digital and the S domain and the Z domain?
Very good question. Now here, when you represent a signal, okay, you can represent. No, this is outside the lab, but I will answer you. Now, if you have a signal, okay, you can represent the signal either in time domain. تمام.
Okay.
time domain شو يعني? I have a signal x of t.
T يعني.
Yeah, x of t equals sine 2 pi t مثلا, like this. خلاص عبرت عنها using time domain. Or
variable
can,
t.
yes, this is called the time domain. Or you can use the frequency domain. Frequency domain الحين I will convert the signal using Laplace transform. So basically we have x of s equals the Laplace of sine t is I think s over x
2 pi over
plus 1, something like this. Whatever.
yes,
So
s square plus
something like this. So I'll say in general Laplace of sine 2 pi t. You know, from theoretical, you integrate this from 0 to infinity to e to minus st times x of t dt, right? So basically here the dt will disappear, and the only function you will have is with respect to
بالتربوع
the s.
بيكون 2 باي على اس سكوير بلس 4 باي سكوير
2
الفاريبل
pi.
بيكون s
Yeah, so this equals 2 pi على
على
S
اس
square
سكوير بلس
1
4 باي سكوير
4 باي سكوير. Okay, thank you. اللي هي omega square على s square plus omega square. Okay. So we know this has some tables. We memorize the tables, Laplace, etc. Now, if the signal is discrete, which I will define now. Okay. Now this is continuous signal, or we'll say continuous time signal. شو يعني continuous time? All right. Now I have defined analog and digital, صح? And all of my explanation was regarding the x-axis here. Okay, but what about the time axis? All right. Now, if your time is continuous, I'll say continuous time. So continuous time شو يعني? Signal value is defined for all values of t. So basically any t you will give me here on this figure, any t that belongs to real numbers, I will give you the value at that t. So this makes the signal like continuous time signal, right? So here, let me plot another cycle. So here, you see I'm plotting a signal continuously, like continuous line. Okay. Now, when I sample the signal, okay, we said here that we have digital converter, right? So the analog digital converter will do two things. This is very important to remember. It will sample my signal at specific values of t. Tamam, you understand? And at the same time, the value of the signal itself, لاحظني, I have chosen only specific values of t for reasons. I'll explain those. Okay, so basically let's explain this before. شو يعني when I take at specific values of t, I'm doing sampling. Okay, let's see the signal. Now when you do sampling, you don't take any t and you take the value on that, you just take discrete values here. You see what I'm doing? I'm just taking samples. This is what will happen when you do, or when you sample a continuous signal. So here I have t equals 0, right? Here, let's zoom. Here what do you have? T equals, now this I will call TS, the sampling period. Here كيف أرسم الحين. Let me just fix my drawing. Alright, so basically this is t equals 0. Here t equals ts. Here t equals what? 2 ts. So basically I am sampling my signal at fixed interval equals ts. Basically I'm taking integer multiples of this ts. I'll explain to you why is this happening in hardware. Okay, so this is discrete point of time. Alright, what about if you take the value of t here. Okay, خلينا أصغر الهات. Okay, so can anybody answer if I take this instant of time, which is between two samples, and between this and this? So basically here
دكتور مش واضح.
الصوت مش واضح؟
اوكي. لا الخط الحين واضح.
الحين واضح. So here signal not defined. Okay, يعني السيجنال هني between two sampling instants is not defined. Okay. Alright, so this is called, we said we have continuous time. Okay. We have continuous time signal. Now when I sample my signal, I have what we call discrete time signal. I hope you are not lost. So discrete time, you take signal value at specific time instance. Okay, Shabab, now I have two things. Okay. Now we have analog signal, we have digital signal, we have continuous time signal, and we have discrete time signal. Okay, let's distinguish between all of them. Now these, the analog and digital, will focus into the y-axis. If I have analog signal, this means the signal value itself, يعني the stress, the strain, wind speed, it can be of any value. It can take any value. While if my signal is digital, no, it will take only from a specific set of values. Okay, Shabab, you understand this? Now when you take the x-axis, the time axis, so all of this is time axis. Is your time continuous or discrete? Now continuous time, خلاص, for any value of time, okay, my signal is defined. So here, give me any t, I'll give you x of that t. Now if my time is discrete, no, my x will be like this. Instead of having x of t, I will have x of, let's put that like this, I'll have x of nts. Now if we take the same example, خليني أكتب تحت like this, same example here, x of nts. What does this mean? It means only at integer multiples of ts that I can find the value of my signal. Okay, so sine, same, let's say 2 pi, instead of t I have nts. Okay, now ts is fixed, the only variable here is your n here. اوكي شباب، مين سأل؟
انا دكتور فهمتك دكتور.
تخربطت للحين ولا لسه؟
والله مو بايد، بس انه قبطني. عرفت، انا حسب اول ان الاس دومين شوي له علاقه في الانالوج او في الانالوج
Yes.
والزد دومين له علاقه في الديجيتال.
لا، الاس دومين for continuous time signal.
والزد
دومين for discrete time signal.
discrete time. اوكي
discrete time. الحين احنا بنركز على التايم. We are just focusing on time. Now being the signal itself analog or digital, الحين شو يصير؟ What happens in the real life? People mix. They say analog and digital, but in their minds they think about continuous time and discrete time. Okay. Now scientifically or from engineering perspective, this is the engineering discrimination. If you are discretizing time, you are working here. So your signal is either continuous time or discrete time. Okay, like this. So if you are discretizing time, now this is my Z domain. Okay, now you say, you don't take Laplace, you say my x of z is defined as you say like this, Z transform of a discrete signal like this, discrete time signal like this. Change discrete time signal. خلاص, it can take x1, x2, x3 samples like this. تمام. Since you mentioned this, خلينا أعطيك إياه. Laplace, نكتب لك يعني. خلينا نعمل zoom. Laplace for continuous time. لاحظ احنا بنركز على التايم الحين، بينما الزد ترانسفورم for discrete time. تمام. اوكي طيب الحين what happens is the following. Okay, this is the big statement that I want you to remember. شو اللون نكتبها like this. Analog to digital conversion will do what? It will discretize time. الحين بشرح لكم شيء عن discretize. And it will discretize the signal itself, both of them at the same time. Now we know when it discretizes the signal, it becomes digital signal, and when it discretizes time, it becomes discrete time signal.
دكتور واضح شو يعني discretize؟ اللي هي تحوله من
تقطع
من الاس ولا التي دومين، من الاس ولا التي دومين للزد دومين.
لا discretizing this is theoretical. يعني theoretical بس practical discretize. I'll tell you what it means. Okay, and why does it happen? يعني ليش يصير التقطيع هذا؟ Okay.
discretize وايد برا.
ما في مشكلة عادي. بس I don't want to ما بدي أخربط زملائك. Like this. Okay. All right. Why does this happen? Why does it discretize the time, and why does it discretize the signal? Okay. This is my topic today. This is very important. Again, I will plot the continuous time signal. Let's plot it like this. Now, my first question to you guys is: the real world, يعني the real signals in the real world, are they discrete or continuous in terms of time? for example, your car speed, is it defined for any value of time or only at specific values of time?
بس يعني
No, I can't hear you.
discrete, بس for very short periods of time.
No, the measurement of your car speed, the speed itself. Yani when you move your car, does it jump from speed to speed or moves smoothly?
Oh لا continuous.
Continuous, صح? The speed itself is continuous. Now your device, unfortunately, if it is the computer, which is true for most vehicles, cannot see this speed for all values of time. So in that sense, the speed itself is continuous, but your measurement will make it discrete. So let me put the signal like this. Okay, so this is, let's imagine that this is my speed. Yeah, let's imagine that this is car speed. So basically car speed itself is continuous. The temperature of your body, is it continuous or discrete? ها شباب؟ Your body temperature. Yeah,
Continuous.
Continuous, right? Because my temperature doesn't jump from 30, 31, 32. No, it moves smoothly through all the numbers. So this is continuous, right? طيب. Now, why does discrete happen? Okay, it's simply because of the nature or the hardware of the analog to digital. Okay, so here, if you put your analog to digital converter, which is called ADC, here I give continuous signal. Here you will get two things: discrete time and digital signal. Alright, why discrete time? Because this can be approximated as the following. If you have a signal like this, imagine that you have a switch like this and you have the other side. Okay, so here I'm giving this signal here, the sine wave I have. Okay, so this is my signal like this. Now imagine each time interval equals TS, you close this switch here. What are you going to get on this side? Okay, instead of having this continuous only while this switch is closed, you will get a signal on the other side. Okay, so basically you'll get, let's say I began from 0. This is the first time I close my switch, I get 0. The second time after TS, so here after TS, I'll get another value. Then after 3 or 2 TS, you'll get a third value like this. Okay, so only at the moment while this switch is closed, you will get values here. Anything in between, you lose data or signal value. Okay, sure. Again, why does this happen? Why the analog to digital converter behaves like a switch like this? Okay, simply because all computers are discrete because they are driven by a clock. Okay, I believe we تفرعنا عن الموضوع شوي. Simply because they are clock driven. And the computers computers are clock driven. This means they change their state at clock or at discrete clock. Edges or instance levels. Okay, Shabab? Now to further understand this, you have to study some computer science, so I'm going to skip that. The summary from all of this is the thing you need to remember is the following. I have analog signal. Analog signal, the value itself can be anything, but the digital signal, the value itself cannot be anything. It can be only, it can take some value of a specific set of values. Now this is the y-axis. Okay. Now the time axis, if you discretize or sample in the time, you'll get what you call discrete time signals. Okay. The analog to digital, خليني أحط لكم إياها like this. The analog to digital will do two things. It will make the signal خلينا نضبط اللون شوي. Now the analog to digital will make the signal digital and discrete time at the same time, both of them. Okay. Why discrete time? Because only at discrete points of time, these discrete points of time, I will have my signal. This is why it is discrete time. And why digital? Simply because it will do something we call digitization. Okay, now these values here will be approximated to some set of values only. Okay. Why is this? Because you have, let me put another reason here. Finite word length will make signals digital بغض النظر عن التايم. Okay, they'll make them digital. Okay, sure. How clear is that? 50% at least?
أكثر عن 50 دكتور، تسلم ما قصر.
Very good. Okay, so if you have 50% understanding, that's good enough. Okay, why? Because we will further understand these principles by applying them. Okay, Shabab? Again, all of these have theoretical foundations and theoretical analysis. If I want to explain, it will become a lecture, not a lab, which I don't like. Okay, and after all, you are an engineer. You want to use a system. Okay, you want to use a measurement system. You want to utilize your hardware. So you need to know hands-on experience, more useful than or as useful as theoretical principles. So we need to focus on this, the hands-on experience. Okay. All right. Let's open the BI now. These are like generic general culture. We will probably come back to them in sensors. I'll explain them, but for now I will not further explain them. Okay. All right. The DAC hardware, we will come back to this. Now let's go to exercise. We already explained this, the analog to digital converter. Okay. All right. I will come back and explain all of this through the exercise. Okay, Shabab. So let's go to exercise number 1, page number 6. Okay. Now this exercise will simulate the action of sampling. Okay. You remember here we said I have a continuous signal and I am taking the value of that signal only at discrete values of time. Okay, we'll simulate this and see some phenomenon or phenomena that arise when you do this sampling thing. Okay, so let's open this VI. It says, the exercise says open sampling simulation VI. Now we have some underlined questions here. You need to answer them in the template. Okay, do you all have the VI open?
Yes, doctor.
Okay, so this is how the VI will appear, front panel. So here I have two things. Plot number 0, this is my continuous time signal. And plot number 1, this is my discrete time signal. Okay, I can see here, this is clear, that only at this sampling instance I can see the value of my signal. Okay, so when I run this, now I can simulate what's really happening when you do data acquisition, or generally the analog to digital conversion. Okay, now here I have two signals, the F signal and the Fs. Okay, what is Fs? Let me put a new tab here. Okay, just a few principles about sampling. Fs, you need to remember this. This is the most important thing today, is to understand Fs and what it means. This is the sampling frequency. It means how many samples you acquire per second. Okay, and I measure it by like this, samples capital S over small s. Okay, this is your sampling frequency. For a realistic signal, if this is your continuous signal, you will discrete, or you will take them like this. Okay, now I know 1 over my sampling frequency is called TS. Okay, and TS is the two samples, or what you call sampling period. The length of this period here is TS. Okay, so this is sampling period. Okay, you need to remember this sampling period and this terminology. Okay, sure, and this relation. Okay, guys. Okay, so here what I have is a real signal with some frequency I can change here, and I'm acquiring this signal at the sampling frequency Fs. Okay, sure. Alright, so here Fs is 50. I have 50 samples per second. This is the speed of my acquisition. Alright, now my input signal, or the real signal, is 1 Hertz. This means I can see here that I have 1 second. The signal will complete 1 cycle like this. Alright, so this is 1 second. I can see it here. Now if you count these samples, the discrete ones, you will find 50 samples. Okay, sure? All right, now let's discover one important phenomenon. Now, if I raise the signal frequency, what's going to happen? Now, I'll fix the sampling speed or the sampling rate, and I will increase the signal frequency itself. Okay, what do you see now? Because I increased my signal frequency, you see more cycles per second. So now in 1 second, you'll see I have here 1 cycle, then 2 cycles. Okay, but then this is 3 cycles, 4 cycles or 4 hertz, and you keep raising. What do you see now? I see 11, 10, etc. You keep increasing. Alright, so I'll keep increasing until 25. Okay, Shabab, can you tell me what do you see? Here, my white signal is the real one, but what can you say about the red signal, the acquired signal?
You mean the FS signal?
The red one, this is the sampled version. Okay, you see here the red dots, can you see them?
Yes.
So what's the value of the acquired signal? Okay, I'll repeat the question, but now in a tricky way. I'll bring this back to 1. Alright, but now I will show the acquired signal, not the real signal. So this plot number 0, I will make the color T, meaning transparent. خلاص, I will not show it. Okay, now if I raise the input signal, okay, now I see only the sampled version of this signal. Okay, so if I keep raising like this, okay, can you tell from this shape that this is like a sine wave? Clearly, this shape here doesn't look like a sine wave, right? I know the real one. The real one, you see, it is a sine wave. The white one. Okay, when I hide the real one, now from the computer side, the way the computer sees the signal doesn't look like a signal. So the higher the frequency, now the shape will be not or far from the real one. Okay, until you get to this critical frequency, 25. Okay, now the acquired signal here is 0. Okay, while the real one, if I show the real signal, it is still there, right? So here this is very important. Although you have a real signal, which is a sine wave with 25 hertz, the computer doesn't see anything. It sees it as 0. Okay, why is this happening? Now if I zoom, let me disable the autoscale X and zoom. If you see now, my sampling instant here equals half of the period of your sine. So basically what you are doing is at time 0 you took the first signal now, or the first sample. Now the signal itself has changed, and at the second sampling instant the value of the signal was 0. The third one, the value of the signal itself was 0. So basically here you are taking a sample of your signal each half period of your input signal. Okay, Shabab. Now if you do the following, if I take the input signal equals the frequency itself, the sampling frequency itself, what's happening? My input signal frequency equals the frequency of sampling, or sampling frequency. This means each time I take a sample, I will catch the input signal again at 0. Between these two samples, the signal changes rapidly, but the computer or the data acquisition system doesn't see this, doesn't see these changes. Okay, Shabab? So you understand the problem? Again, for low frequencies like this, if I put 1 Hertz, okay, my acquisition is good. I can see the shape of the signal. But when I raise the input signal frequency, I start losing information. All right. Okay, Shabab, do you understand, or does it look unclear for you?
Yes, we do, Mr. Ali.
All right. So, why is this okay, let's see. All right. Now, theoretically, I'll explain to you theoretically like this. Theoretically, I have x of t equals sine 2 pi times f of my signal, which is f signal here, okay, times t. Now when you sample your signal, you get not any t, only at integer values of ts, like this, and this will be equal to sine 2 pi f times, now instead of t here, I'll put nts. This equals what? Sine 2 pi times f times n, because I can write ts as 1 over fs. Simply I can put fs here, right? Okay, so what happens here at this value, when you put this as 25, okay, you see this critical frequency. Now, f over fs here in the equation is equal to what? Say at f equals half fs, you'll have x, let's say x of nts equals sine 2 pi. Now, f over fs is half times n, right? Are you following? Now this equals what? Sine. Now 2 will go like this, sine pi times n. And what does this equal, Shabab? Integer multiple of pi. What does this equal? 0. So this is 0, right? So I have a signal. It has a frequency of 25, but when I sample it on the computer, I see 0. Okay, and this is my red dots here on the graph. Okay, Shabab. So what does this mean? If you choose some sampling frequency and fix it, you have a limitation on the input signal frequency. Okay, Shabab, you understand this point? So this means one thing here. Okay, Now, there's a theory that explains this. It says Nyquist sampling theorem. It's very simple. Now, the summary of that theorem is that the sampling frequency, fs, should be greater than 2 times the signal frequency. And please remember this. Okay, sure. So this means if I fix my signal frequency, I should sample with more than 2 times of that signal. Okay, shabab. So here, let's see. If I fix the signal at 25, my sampling frequency should be more than 2 times. So here it doesn't say equal. There's no equal here. Okay, so this means at least you have to raise this above 2 times this. Okay. Now, this is the minimum or the critical value, 2 times. You see now here that I'm measuring the frequency of the input signal. The input frequency is 25, I'm measuring 25. Okay. So for frequency measurement, this is fine, but for shape restoration, this is number 2. To represent signal shape, the sampling frequency should be 5 times, or at least 5 times, the input signal frequency. Usually we use 10. Okay, shabab. So for example, the electrical mains from the outlet here in UAE, I have the following signal. You have 240 volts times sine 2 pi. What's the frequency شباب on the mains? يعني الكهرباء اللي تيجي من from the wall. What's the frequency?
I'm not sure about the frequency, and I know the voltage is.
Yes, the voltage is 240, right?
Yeah. Okay.
The frequency, any device you see here in UAE is, let me show an example. How can you know? Next lab, probably I will explain to you, or I'll show you the frequency of the mains. Just 1 second. There was a draft like this. Next lab, okay. Alright, this is a laptop power supply. What does it say? It says the input. It says the input here is from 100 to 200 volts AC. What about the frequency?
50-60.
50-60. So 60 is usually USA. I think Japan is using that, but here Europe and Middle East they use 50 hertz. 50 hertz. Most of the world countries they use this. Middle East. Okay. This is why if you buy a device from USA, you should be careful that it can withstand Middle East or the regional electricity. Not all devices take this. So the USA is usually like this, 100 volts or 120 and 60 hertz. Okay, so basically this device can fit anywhere on the world. Okay, now the frequency that we receive is, where is that? 50 hertz. So I can put 50 here times T. The question is to have a good shape for the signal, what's the minimum sampling frequency I need? Yani fs equals what?
101.
101, but satisfying this rule as well, to have a good shape, you need 5 times the input signal. So 5 times 50, right? So you need how much? 250 what? Samples per second. We can try this. If I put the input signal as 50, come on, where's the keyboard? Hope this is 50. Okay, and I should put here the sampling as. Now what happens if I put it the same, 50-50? You'll see 0 here. Okay, the acquired is 0. If you put 100, is that good? Exactly 2 times this, which is not good. I see 0 again.
Yeah, we still get 0.
Still get 0. Why? You can use the equation. That's very simple. So I'll get 250 at least. Alright, maybe it looks like a sine wave. So again, between 5 and 10, the rule says between 5 and 10. I usually use 10 times. 10 times. Oh, not 10 here. 10 times and 500 samples per second. Okay, maybe this will look like better like a sine wave. Alright. The end result of this, what you need to remember is, you have a signal and you're sampling that signal with a speed, with specific speed, samples per second here. Okay. If you put very high sampling rate, you will waste resources because you need a fast acquisition. This means your computer should be fast and your software should be very fast. So you'll waste resources. Okay. And if you put slow sampling rate, as we can see here, you can misrepresent your signal. We have seen if this is very low, you will misrepresent your signal. Okay, sure. So what you need to answer in the template is make fs 50 Hertz and the signal as 1 Hertz and provide a capture for this. This is easy. Make the signal 51 Hertz. Now answer this, is the sampled version same as the original? Let's try this. F signal, I want 51 Hertz. And I will keep the sampling as 50. Okay, so at this configuration, what do you see, Shabab? I see that my frequency of the signal itself is 51 Hertz. But what I see here is 1 Hertz. Okay, Shabab? So is the sampled version same as the original? What's the answer, Shabab, for this one? So basically the answer is no. The sampled version, here the sampled version shows that my frequency is 1, while actually the real signal has a frequency of 51. Okay, so basically 51 hertz will appear as 1 hertz, simply because my sampling frequency fs is actually less than the frequency itself. Okay, while basically it should be more than 2 times. Okay, so this answers this question. So if you make the signal as 101 hertz, what does this show? Let's try this. 101. Okay, I see the real signal has changed, but still what you measure here is 1 hertz. Okay. So basically 51 hertz and 101 hertz, both of them appear as 1 hertz. Okay, this is the critical thing, is that you have a limitation on the input signal frequency. Okay, fixing the sampling frequency. All right. Okay, very nice thing we see every day, not every day, but from time to time, is the following video. Okay, now this is a YouTube video which will show you what we call the wagon effect. Okay, Shabab, so if you blink, now we see this very often. The car here is moving, but if you look to the wheel, it doesn't look like moving, right? Who can explain this? Why does the wheel look like fixed?
Has to do with the frequency of light or something like this.
Yes.
How frequent we see frames per second.
Exactly. So here you have a camera, right? The camera is taking, usually cameras, they take how much? They take 30 frames per second. 30 frames per second, or this is the sampling frequency. Frames per second or sample per second is the same. Okay. Now, if the wheel is moving here, the wheel is moving at multiples of this frequency, it will look like it is fixed. Why? Simply because the wheel is moving like this. So each time you take an image, you capture it here. The next time it will move. The next image will capture it here. Then it will move. The next image will be here. So all of your images, you will see or you will capture the location, the wheel at a specific location. Okay. So here you can conclude that the speed of the wheel is like multiples of the for the frequency of the sample. Okay. So this is very fine. So strangely here they could capture it really well, which is very hard. Sometimes it appears moving backward. Why is that? Okay, so I will leave this to you to think about. Yeah, the wheel is moving forward. When you sample or when you take a video for that wheel, it will appear like moving backward. Sometimes if you look at it, even without a camera, it will appear like backwards. Okay.
Maybe because the wheel is moving very fast.
Very fast, but why backwards?
Because
It's tricky, right?
when it completes before it completes one rotation, like we get to see it twice, something like this. I can't explain it, يعني, but I have an idea in mind.
Yeah, you feel it, but
yeah, I can't explain it.
Yeah, it is something like this. So if the wheel is moving, you take the first image here, it moves. The second image you took here. So it appears like it has moved backwards slightly. Next time it moves, you take here. Okay, so basically your wheel is accelerating or deaccelerating. So each time it appears like this, so it appears like moving backward. Okay. All right, so this is you can explain these phenomena using this sampling principles. Okay, so same here. When I run my VI, if I put basically 50 and 50, this is similar to the wagon effect. The signal exactly at the same location. Here one cycle, I capture it here. Next time, I captured it at 0. So to me it appears fixed, like DC or like 0 signal, while it is really moving. Okay. All right. So makes sense for you, and I don't want to complicate things. If I really did not complicate them, by the way. Now, Shabab, anything about these questions? You understand, or you know how to answer them? All of these underlined questions, you have to provide answer in the template. All right, digitization. Now, this is optional. I will skip this. This explains a little bit about digital signals. Now, all of this, the sampling, I discretize the time, or the I'm doing what I'm having actually is discrete time signal. Okay. Right. So on discrete time signals, you will care about the sampling frequency. Now, if you digitize the signal, that's something else. Now you're converting the signal to digital form. Now this is a digital signal. Then you will use a number of bits to represent the signal, and this will have a limitation on the y-axis, basically your resolution and the minimum measurement you can achieve. Okay, but I will skip this. Right? I'm not going to explain it. So exercise 2, you can skip. Shabab, question? Right, so I will jump directly to practical analog input. Okay, so this is where we will connect to our hardware, and basically this is where the fun begins. Okay, any question before we begin with practical analog input? All right, so what I will do here, I will utilize the Elvis board here in the lab. I'll show you how to connect to the board remotely, and we will generate a signal. Now here in the simulation, I'm doing everything actually in software. You'll see that I am creating a sine wave with 0.1 sampling time, and another one with the time I'm using here. Okay, so this is simulation. Now we'll see for real. Are these really true, the things that we simulate, or not? So I will generate a signal and then display it or acquire it using oscilloscope. Right, so the first thing we need to know is we have defined signals, right? Where's the signal? Okay. So we know a signal is a physical variable that changes with time, right? It changes with respect to time. The device that will display this signal with respect to time is called oscilloscope. Okay, so basically it's a scope that shows oscillation. This is the historical name of the device. All right. Now we need to work in parallel. I'll show you how to do the configuration for the device, how to get some of the measurements, and basically you'll have questions here that you need to fill in the template. These are the underlined questions here. Okay, sure. Let's open this web page. This is step number 1. I need to open this web page. Okay. So to open it, you need Chrome. Don't use Firefox. It's not going to work. You will need Google Chrome. Okay. So I'm going to open Chrome. Basically, I will paste this link here, and I'll see this web page. Okay, sure. So can you confirm that you can see this web page?
Yes, you can see.
Nice. Anybody doesn't see this web page? All right. Now I'll click on measure. هذا مش clear. Okay. So here I have 2 choices to connect to the Elvis board. Now if I'm present near the board, I'll switch to camera and show you now. How can I maximize my camera? I don't know. Okay, so if I'm near the board here itself, you can see that I have a USB cable, and I can connect this to okay, so this is my USB. Kishab, is the image clear?
Yes, Mr. Ali, we can see. Not very clear, but yeah, we can see.
Okay, clear enough. Okay, so USB, you just connect it to your laptop, and then you can connect through that. Okay, now I have another choice. I will connect remotely to this board. Basically, I will go to network here. Okay, let's switch back to the screen view. In the network here, you need 2 things: the device ID and your name. Okay, now device ID is a unique ID for each board. Okay, and that changes daily. Okay, you need to remember this, that the ID is changing daily. Okay, so the IDs we will use today, tomorrow they will change, and I will update you with the IDs. Okay, so let's get the available IDs for today. All right, so today I have these IDs. Okay, all of them begin by an I, capital an I, and then some number. Okay, so I'll share this with you, and you can use any ID. Okay, let's copy the link, and I will paste it here on the chat. Okay, so this sheet will update daily. Okay, so just select any one of them and enter it here. Okay, and you'll see what happens. We'll have some clash, but this is fine. We will see how this is working. So I'm going to select the first one. Okay, Shabab, are you following? I'll put it here and put Ali work. And then I will connect. Oh, it's not working. What happened? Ah, I see it has already changed. So I'll update you the new one. Okay, let's update. So this is not valid anymore. And I 1P. how do I get these IDs? Basically, if you switch to camera, now you see in front of you, this is the board and there's a screen here. If I press a button here, now the small screen will show the device ID. I'm not sure how clear is that. Let me just turn off this light here. Okay. So basically here I see there is a device ID and I need to get or update this daily. Okay. And I1PZR. Okay, and I1PZR X9W0. X9W0. Sure. Okay, so I've updated the first one. Let me try to use the second one. Check that. Okay. Okay, Shab, so how clear is that? Are you following?
Yes, Mr. Ali, معك.
Okay, so anybody has a problem connecting to the device, because this is what you will do by your own. And I will leave these IDs for you at any time. Just put an ID and connect and complete your exercise. Okay, so you have to have this working. So how do I know if I'm connected? Here you will see that you have an iLBS3 and some serial number to that device. Okay, so here on the right, okay, we switch back to the screen. I see it says click here to add instruments. So if you click this one here, now you have a lot of instruments that you can choose from. Okay, now here under this I have oscilloscope and function generator and arbitrary waveform generator. And here I see available. It means that nobody is using these and you can use them. Okay, what if someone is using them? Let me try to do that. Okay, خلينا نشوف device number 1. Let me just disconnect. Okay. Oscilloscope and function generator. So basically, I need to run both of these instruments, the oscilloscope and function generator. Nobody is using them. This means I am the only one active now. Okay, guys, I need someone from your side to access these steps. It's important. I'll show you what happens if multiple users access the same board. Okay. So can you please access the first one, device number 1. So I will know when it works from your side, because this will change. Okay, the list of current users will change.
Mr. Ali, can you show us the steps again on how can we access?
Okay, from scratch. I'll open Google Chrome. Tamam. I will go to this web page. Okay. I will go to measure. Tamam. And the network. Now I'll paste one ID of these. Okay, I'm going to select the first one. Okay, شباب, following. So this is ID number 1. I'll put my name and I'll connect. Okay, now I see it is connected and you have here a serial. Now from these instruments, you have a lot of instruments here. You have digital multimeter, variable power supply, data generator, whatever. So today I'll need the oscilloscope and the function generator. Okay, شباب? Alright, somebody has... Alright, very nice. So المناعي is viewing both of them. صحيح?
Doctor, I cannot access it.
What does it show
Yeah,
on your
it's
side?
giving me invalid device ID.
Yeah.
لا,
مناعي-
I have updated the ID 9W0.
Which one should we use? مناعي, which one did you choose? 1 ولا 3? Oh,
مناعي اختار 1.
okay, Mr. You took 3?
I took 1. It's okay, you can use 1. I will show you what happens if you have multiple users.
Okay, I'll access now.
Now these will change daily, so probably tomorrow they will not be valid. I will update you with new ones.
Which instrument should we choose? And it showed me a lot of instruments: oscilloscope, function generator, data generator.
Yes, so you will need scope and generator.
Okay.
So this step is important, so I can... Yeah, Karim, I see you now. Okay, so you all have to be good with this step. Alright, now if you switch to my screen now, you'll see that you have multiple users here on this instrument. Okay, and here if you click on the users, you'll see that Ali work controlling, Manna viewing, Karim viewing. This means I have control over the device, but you guys will see the results on your screen similar to what I will see. Okay, now our release control, this means anyone of you can have the control. Okay, for example, Manna'i, can you control the devices? Both of them? Okay, now Manna'i controlling. The same for the function generator. Okay, Manai, can you control the function generator as well? Or Karim, any one of you? Okay, now Karim is controlling the function generator. Al-Manna'i is controlling the oscilloscope. This means the rest are viewing. Okay, Shabab, you get the point?
Yes.
Okay, so Karim, can you run the function generator? And Manna'i, can you run the scope?
Should I keep the numbers the same?
Yes.
Okay, I hit run.
Okay, now the rest can join, but they will be viewing because other users are controlling. Okay, now this strategy we have...
Doctor?
Yes?
When I try to connect, it always says connection failed.
طيب
Abdullah, حاول make sure it's network مش USB. And I did this mistake in the beginning.
Network حاطنا.
Network أي ID أنت ماخذ؟
The first one.
طيب can you share your screen؟ خلينا نشوف شو المشكلة.
اوكي كيف الحين شو share screen. Request control.
لا شير من التيمز
Okay.
just okay. So here in network شو دخلت NI NI1P ZR W0 في space تأكد إنه ما there's no space.
Between what?
ال ID آخر شيء ممكن يكون في space. Nothing. طيب your name can you put عبد الله الرحمن. طب connect. Limit. لا I don't think so because I tried this before. طيب can you put another ID? Let's try the second ID. So the second ID currently is this one. اوكي عبد الله شو صار معك؟
I will try now. أشوف.
Which browser are you using?
Chrome.
Can you go back to the page?
Still same problem.
I didn't see your page.
Oh, you can't?
طيب connecting to device. طيب let me try from my side. استعملت VQ اللي هو the second one using Chrome. Okay, I will go back. I will leave this measure network. This is here. Okay, from my side it works. But can you try using a new window, Google Chrome new window?
Okay, I'll try.
Because the first and second they are working, so it should be working on your side as well. Okay, now only Kareem معي على device 1.
Still the same, doctor. Even I don't know في حد غير يعني.
طب show me your screen. Let's see why this is happening. Okay. Exercise سهل. We have time. Okay, signaling server. Can you hide this signaling server?
Which one?
Yeah, this here. Daily control. Yeah, this one here. Just hide this one.
Okay.
Okay, your name